proposal of vote of thanks. Without wasting much time, I request the principal of our college, Honorable Dr. V.S. Sawant, sir, to welcome the dignitaries and participants through his welcome note. Honorable Principal Dr. V.S. Sawant. Over to you, sir, Dr. V.S. Sawant. Over to you, sir, please.
Good afternoon, all. Distinguished guests, participants, dear colleagues, ladies and gentlemen. It is a true pleasure for me to welcome you to the international webinar on hyphenated techniques in detection of smart materials, organized by Internal Quality Assurance Cell and Department of Chemistry, DP Bhosle College, Koregaon, Satara District, Maharashtra, India. I am very grateful to Dr. Pradip Pachfule, post-doctoral fellow, Department of Chemistry, TU Berlin, Germany, for taking time off from his busy schedule to resource this webinar. I also wish to welcome and thank Dr. Deepkumar Joshi, Department of Chemistry, Sheth M Science College, Patan, Gujrat, for accepting our invitation. The webinar is also cherished by Honorable Principal Dr. Pradip Gaikwad, Joint Secretary, Higher Education, Rajya Shikshan Sanstha, Satara. Our college is established in 1968. We provided quality education in science, arts, commerce, computer application, and BO streams. At present, 3,460 students are studying in the college, with 15 undergraduate and 7 postgraduate programs. Besides, the college offers career orientation certificate program and 19 short-term courses. Our college has been accredited A grade with 3.12 CGPA. It also certified with ISO 9001:2015. I am especially honored to welcome you all in this digital platform of DP Bhosle College, Koregaon. The theme of this webinar is hyphenated techniques in detection of smart material. As we are going through the pandemic period and with a fear of COVID-19, the inevitability of smart materials is once again emphasized. PPE kits, gloves, goggles, and the most unavoidable face shields, masks are the necessities nowadays. Many of these in variety of materials are available in the market and also online. The trustworthy material needs trademark brand, which can only be obtained only after the rigorous analysis. The topic for the webinar is shaped with thought in which it mentioned. This creates an opportunity for the participants to hear of the recent development in the field of analysis and smart materials. As you all know, the frequency of webinars all over the world increased so much that it is now very difficult to decide which webinar to attend. Still, in all, we have about 1150 plus registrations from all over the India and from the abroad. I must appreciate the efforts taken from our team. For the first time in this academic year, our faculty from chemistry department has worked together to put an academic program that I am sure will satisfy everyone's requirement. On the behalf of Rajya Shikshan Sanstha and DP Bhosle College, I welcome you all and wish every success for this webinar. Thank you.
Thank you, sir. Thank you for your introduction and welcome note. Am I audible, Dr. Kosti? Hello.
Yes, sir, you are
Hello.
audible. You are audible, sir. Continue.
Okay. Thank you. Now I turn towards the inaugural event of this international webinar through the inaugural talk of the special guest to let you know that Honorable Principal Dr. Pratibha Gaikwad ma'am is an eminent academician. She has a very huge experience of working as the principal of affiliated as well as autonomous college. Ma'am is a stalwart scholar in the subject of economics. She has worked as and is still working as NAC assessor and visited most of the Indian states for the same purpose of NAC assessment of colleges. Ma'am is a member of Managing Council of Shivaji University, Kolhapur, and most importantly, ma'am has recently taken the charge of the Joint Secretary of Right Section Sanstha, which is one of the largest education institutes in Asia continent. I'm sure that Dr. Gaikwad ma'am will definitely raise the quality culture of higher education with her visionary plans. Ma'am, I take this opportunity to congratulate you on behalf of our college and all my colleagues. I wholeheartedly welcome you in this webinar and request you to please proceed with your message. Honorable Principal Dr. P.S. Gaikwad, ma'am. Over to you, ma'am, please.
Thank you, sir. A very good afternoon to one and all. It gives me
Thank you.
immense pleasure to offer my heartfelt tribute to the founder of Rayat Shikshan Sanstha, Padma Bhushan Dr. Karmavir Bhaurao Patil and Rayat Mauli Sau Lakshmibai Bhaurao Patil. Our distinguished principal of a very renowned D.P. Bhosle College, the college which has obtained A grade, Honorable Principal Dr. Sawant Sahib, all the resource person and dear participants. It gives me great pleasure to be amidst you this fine morning. The D.P. Bhosle College today has organized a very meaningful international activity, that is international webinar on hyphenated techniques in detention of smart materials. It is an international webinar organized in collaboration with Technische University Berlin, Germany. Indeed, it is a very, very praiseworthy activity which has been carried out by D.P. Bhosle College under the eminent leadership of Honorable Principal Dr. Sawant sir. Sir, this seminar would be of great importance and relevance to all the academicians, not only in Maharashtra, but in the nation and worldwide. I appreciate the fact that we have 1150 participants enrolled for this very well received seminar. So on this occasion, on behalf of Rayat Shikshan Sanstha's D.P. Bhosle College, I declare this international webinar as inaugurated, and I offer my best wishes to the resource person and all the audience throughout the seminar, and I wish all the best to everybody. I thank Honorable Principal Dr. Sawant sir for honoring me by giving me an opportunity to inaugurate this international activity of great relevance and meaning. I appreciate all the staff of D.P. Bhosle College for organizing this wonderful activity. Thank you once again. All the best. Thank you, sir.
Thank you, madam. Dr. Lokde, sir, please.
Thank you, ma'am. Thank you for having and as organizers with your valuable inputs. Thank you very much, ma'am. Now, the session first will begin with the introduction of the resource person, Honorable Dr. Pradip Pachfule, and for that purpose, I invite
डिस्कनेक्ट झालं बघ डिस्कनेक्ट झालं
Madhav, sir, you can start.
ओके
Madhav,
ओके
sir,
ओके
please.
Welcome to participants from all across the world. I am very much thankful. I am Professor Dr. S.D. Zadav from D.P. Bhosle College, Koregaon, Department of Chemistry. Really, I am honored to introduce one of the great personality in research field, Dr. Pachfule sir. He belongs to native place from Pandharpur. He did his BSc in 2003 in Shivaji University, Kolhapur. He did his MSc in 2006 from Solapur University, Solapur. He acquired PhD degree in 2014 from NCL, Pune. As far as awards are concerned, he got Best Research Scholar in 2014. He got SPS Postdoctorate Research Fellowship in 2016 from Japan. He also awarded Alexander von Humboldt Postdoctorate Research Fellowship in 2017, and at present he has been working as a postdoctoral research fellow in Technische University Berlin, Germany. As far as publications are concerned, he had published more than 60 international research papers like Journal of Chemical Society, Nature Chemistry, Chemical Communication, and so on. As far as skills acquired are concerned, he is very much prominent in covalent organic frameworks, photocatalysis, hydrogen storage, energy storage, porosity, and metal organic framework. So, with his topmost biodata, I expect from this resource person, because the area selected, that is analysis of smart materials by means of hyphenated techniques. So definitely all the participants are awaiting to his talk. So I would like to hand over to today's speaker, Dr. Pradip Pachfule sir. It's over to you, sir.
Okay, thank you, Dr. Jadhav. It's a pleasure to be here, and good morning to all of you. Thank you, Dr. Sawant, for such a wonderful organization, Dr. Lokde, and I would thank Dr. Koste as well for the invitation and organizing such a nice event. So it is a pleasure to see that all of these things are happening very nicely over there, and during this time where everybody is struggling to get the things on the right place, we are doing something which is important for the scientific community, and I'm happy to be part of this particular event. I'd like to thank Dr. Gaikwad as well as all the members of this organizing committee for giving me opportunity. And as a part of this particular presentation, I will try to take you to the journey of some of the interesting materials what we are working on in TU Berlin. So I hope I have 40 minutes, so I can just try to finish as much as. Okay, so again, good afternoon, everyone, and thank you again for giving me opportunity. And as a part of this webinar, I would like to give a particular presentation on personalized covalent organic frameworks for photocatalytic hydrogen generation, which are next generation smart materials. And in today's era, when we talk about everything, in today's era, when we talk about everything, materials related to energy and generation, emission-free fuels are getting much more importance. And the reason is that because of what we see in general is that because of the pollutants which are emitted during the fossil fuel burning, they are really getting much more impact on the atmospheric conditions. So myself, Pradip Pachfule, I'm working in TU Berlin as a postdoctoral research fellow from last 4 years. And this is more or less how our campus looks. And here's somewhere here we have our somewhere here we have our lab, and this is the overall campus. This is main building and all other the campus is more or less distributed in all over the city in center of the Berlin. So with this, I would like to start my presentation. And so when we talk about the smart materials, so which materials can be said as smart materials? The materials that have one or more properties that can be significantly changed or controlled by external stimuli are called as smart materials. External stimuli means that could be pH, that could be temperature, that could be pressure, or there could be multiple factors which can deform this material. But most importantly, the important factor over here is when they deform, they should come back to the original state when you take out that particular stimuli in there. So for example, some of the computer chips which are made from the silicon, the glasses which changes color as soon as you go out in the light, they become dark. Some of the jackets which can be cooler when you go into the sunlight. And there are so many things which are nowadays getting involved and getting explored. And many of these things are related to us. We are using many of these things in regular life. For example, all of us have the mobiles, and the next generation of mobile could be the mobiles with foldable screens. And this could be coming out from the smart materials. So the next generation of the material would be the materials which are exactly smart materials. And in these materials, when we talk about the external stimuli, most of the time, these external stimuli such as humidity, as soon as you come in the contact with water vapors, magnetic field, temperature, light, and pH, they start swelling or change their shape, and they stay self-assembler. They start self-assembling each other. But the important factor over here is it's just not one-way interaction. This has to go back to the original state. Then only we can call these materials as smart materials. And in that particular state, just for example, when you take a hydrogel, you put the water inside, they start swelling. And once you take out the water, they will go back to the original state. So you can do multiple cycles back and forth, depending on the flexibility and characters of those particular materials. So few examples which we regularly see around us. So you have a spoon which changes color as soon as that comes into contact with the hot coffee. So this is a regular life examples, and this is the actual implementation of the smart materials what we see in regular life. And most of you are known about the sunglasses. As soon as when you are inside the dark situation, the glasses will not be dark, but as soon as you go out in the sunlight, you will start seeing as a darker frame of your sunglasses. Next, these nitinol wires, which many of you would have heard about it. So they bend to any shape, whatever you like. You put in the cold water, nothing happens. But as soon as you start putting them into the hot water, they start getting back their original shape. And most importantly, this is the example which is known for the many of us. There are hydrogels in which we can put the plants, and this will slowly release the water, whatever is necessary to grow the plants. So these are the real-time practical applications of smart materials which we have seen. I'm not talking much about the biological application, where there are so many applications in today's era which are considered as a smart, which are given by the smart materials. So all of you know there are so many materials on the smart materials, but I will talk a bit about the carbon-based smart materials, because the current era is more or less about the carbon. After the first discovery of the graphene, this era was even expanded into more and more significantly. So there are three different types. Basically, there are four different types of carbon-based materials, depending on what kind of dimensions these materials have. So these carbon materials could be 0-dimensional, 1-dimensional, 2-dimensional, and 3-dimensional. So if I have to give a distinct example, carbon onions or carbon quantum dots, which all of you would have heard of, they are 0-dimensional material because they cannot extend into dimensions further. But when it comes to the 1-dimensional material, these are carbon nanotubes, which we have seen nowadays in everywhere here and there. The best example could be the bicycles, which are lightweight bicycles, which are composed of the carbon nanotubes. But 2-dimensional are the graphene. We are generally seeing graphene in several optoelectronics as well as in the mobile phones and so on and so forth. But when it comes to the 3-dimensional materials, And here we have some of the smart materials which are pillared graphene. So their graphene sheets are, two-dimensional graphene sheets are connected with each others by the pillars. And the second part of this materials is the aerogels. Aerogels which have they keep the water inside, and when you take out the water, they keep the big sized pores which can be used for the multiple applications. And the last and most interesting part of these materials is metal organic frameworks. So these are three-dimensional materials. I will come back to this one, but I'm just reminding you over here, just keep eye on one word, metal or organic framework, because these are the next generation three-dimensional materials which are going to be much more importance into many fields. And when it comes to the structure, how does this happen in the two-dimensional, three-dimensional materials? These are the carbon atoms which are covalently attached to each other through the strong covalent bonding, which is unbreakable. And that's why you see these carbon materials are highly stable at any chemical conditions. And these layers are held together by weak bonding force, and which can be exfoliated, giving out some of the nanoflakes or one or two layer graphenes, so on and so forth. These materials have many advantages. As I already mentioned, they are lightweight, their density is very low, they are porous, and they can be used for multiple applications. But these materials have some of the limitations as well, because when it comes to zero-dimensional material, we always see the agglomeration of these materials. When it comes to the carbon nanotube, these materials generally see the low packing density, which generally hampers the applications of these materials. And in two-dimensional graphene, we generally see either there are problems with restacking. Once you exfoliate the material, you generally see that these materials start the restacking first. But sometimes it's really hard to get the one single sheets out of the graphene as well. And in three-dimensional material, there are some problems regarding design, stability, and manufacturing. But design means how would you design these materials? Second is stability, chemical stability I'm talking about, and manufacturing, because these are complicated procedures which we need to follow when we think to synthesize this material. But all of these problems can be solved using metal organic frameworks, which I will talk in just another minute or so. So when we particularly, I would not go other materials, but when it comes to the materials such as graphene, so what are the best properties of these materials, and how would you characterize those? I will go one by one so that you will get more and more understanding of these materials. They have atomic thickness. We generally do the graphene nanoribbons are just having 0.335 nanometer thickness, and which we can characterize using different techniques such as TEM, SEM, so on and so forth. They have high electron mobility, which gives their application into the optoelectronics and other electronic applications, and which can be measured by normal measurement techniques. They have good strength, they are defect free, and once they are attached to each other, they have very good strength, and which can be done by normal physical methods. They are very tough, as well as their stretchability is high. They have very good stiffness, and most important, they have very high surface area. Some of the materials which have been reported till now having surface area of 2,630 meters square per gram, and this is going more and more into the even more higher values. And this can be measured by the BET analysis, which generally we do in the lab at 77 Kelvin, 1 atmospheric pressure. They have impermeability. Even the smallest atoms such as helium cannot permeate through, and this could be one of the options to purify water, which gives this material another advantage. They have good electrical resistivity. They have fantastic thermal conductivity, which actually gives applications of this material into many avenues. And then they have transparency, and that is why we see the utilization of this material into solar cell, so on and so forth. So due to these properties, these materials have been applied into different ways. For example, just when we talk about the graphene, there are different type of graphenes. So there are some of the graphenes which show the structural deformation. These we call as intrinsic graphene or graphene ripples, which can change their shape according to the necessity of the application. Then there are contact resistance. There are graphene nanofilters, nanopillars, and graphene woven fabrics, as well as graphene networks, which have contact resistance with each other. And then last part of the graphene material is the tunneling effect, and these are called as graphene islands, which generally shows the applications in multiple places. So because of different various properties, as well as various types of graphitic materials. These materials have been applied for the many places. And just to take you on the journey of these materials, where these materials have been applied. For example, all of us had flights sometimes, and nowadays to make these vehicles, for example, Boeing is using carbon nanofibers and graphene to make the planes and some of the spare parts of the planes, because these are very lightweight materials, low density. In mobile phones, for example, next generation mobile phone would something like this one, very transparent, but they have some conductivity because of the graphene, and that's why we can do multiple applications. And this material have already been applied for DNA sequencing, computer chips, and most importantly, currently these materials are getting applications into prosthetics, flexible screens as well. And currently many materials are getting applied into solar panels because of their flexibility as well as good conductivity in a prospect. So graphene materials are very good, very fine. They have multiple applications, but there are issues with these materials which need to be addressed. And some of these issues are, these materials are not ordered at all. What I mean by ordering is that we don't know how these graphene sheets are organized. Like there might be possibility that one graphene sheet is like this and other graphene sheet comes in between as in a 90 degree. But that's why we don't know where exactly these atoms or particular metal or particular functionalities are present. And to avoid that, it is better to have the material which have the crystallinity. Crystallinity means a particular order through which you can go ahead. And next part is porosity. We know that these materials have some high porosity, but there are different kind of pores. Like there could be macroporous, they could be microporous, they could be even mesoporous as well. And they don't have tunability. For example, if I want one material having the pore size of say 2 nanometer, I can't synthesize exactly 2 nanometer or 4 nanometer or 6 nanometer, depending on the necessity of application. So when it comes to the porosity, as all of us know that according to the IUPAC nomenclature, materials can be classified into 3 different parts: macroporous, mesoporous, and microporous, according to what pore size these materials have. And if we look into the literature, we generally see that there are a couple of methods which have given the reproducible result, that is direct printing. In this case, you have a template on which you can put the filter, on which we can infiltrate and polymerize some of the polymeric material, make the carbon out of it or make a polymer out of it, and remove the template to get the material with precise pores, size, and composition. Similarly, many of us has heard that block copolymer self-assembly, wherein you have different micelles which gets organized in a particular fashion, giving out the polymeric material, carbons as well as porous material, including silica, carbon, and so on and so forth. But since these materials are working in macroporous and mesoporous region, what we generally see that direct templating as well as block copolymer self-assembly works very nicely, because pore size is beyond 2 nanometer to beyond like 50 nanometer, 100 nanometer, close to that particular region. But when it comes to the microporous region, where your pore size has to be just 2 nanometer, that is 20 angstrom, which is really hard to manipulate. In this case, the only leftover option to synthesize this material is direct synthesis. And what I mean by direct synthesis is, when you have to synthesize the microporous material, you have to coordinate metal centers with organic linkers to just synthesize the materials with precise porosity. So the first example could be zeolite, where metal centers are coordinated through oxygen with each other, creating the microporous material. And in metal organic frameworks, for example, metals are coordinated to the next metal through the organic linker. And in covalent organic framework and porous polymers also, organic linkers are coordinated with each other through the covalent bonding. And that is why you can maintain the porosity depending on what kind of pore you would like to have, what kind of materials you would like to have. And this can be just tuned by changing the metals or organic linkers. But when it comes to the type of materials, inorganic materials are known from years, and all of us are aware of the fact that zeolites are first known microporous materials. Carbons were known from centuries, but they are not purely microporous materials in a way. So if I'm not wrong, every drop of gasoline or oil or petrol or diesel we use, that passes through the zeolite. And this is the application of zeolite what recently has shown, and this is one of the application of microporous materials. since they are very smart, these materials can be applied into multiple applications. So there are several materials which are known from the zeolite, which are completely inorganic, and recently known materials are the organic materials, which are called as covalent organic frameworks and microporous organic polymers. So I will be more or less talking about these particular materials because these are the materials which are really smart and which are having different properties, which I will come back in a moment. But these are the materials which can be applied into multiple applications in near future, and that's why they could be called as smart as well. So among these two classes, which are completely inorganic, where we have zeolites, and then we have covalent organic frameworks and microporous organic polymers, which are completely organic. But there is another class of material which are called as metal organic frameworks, which are hybrid materials, which have metals from zeolitic side, which are inorganic, and organic linkers from the organic side, which are covalent organic frameworks or microporous polymers, forming hybrid materials. And as the name suggests, these materials are metal organic framework, where metals are coordinated to the organic linkers, forming the frameworks. And similarly, in covalent organic frameworks, only linkers are coordinated to each other, covalently attached to each other, forming the porous materials. And among these, zeolites, MOFs, and covalent organic frameworks are the crystalline material. If I remind you back, I said that what is meant by ordering. So I was talking about the ordering in here, because these materials, we know exactly where is metal sitting, where is linker sitting, where are the functionalities has been placed in. So this is why these materials can be useful in multiple applications, including catalysis. So how does metal organic frameworks get synthesized? So if I'm not wrong, I have already said that metal linker, metal clusters, any metals from, you just pick any metal from the periodic table, start coordinating with the linkers which have two type of coordination sites. So in this case, metal cluster starts coordination with the organic linkers, forming elementary units. In our language, we call it a secondary building unit, which goes on extension into three-dimensional, giving on the metal organic frameworks, which are porous, crystalline, and have various functionalities in their backbone. And now, since these materials are made from metals, you can use these metals for catalysis. You can put some functional groups on these linkers, and you can have the functional linkers which can be used for various applications. So how does this material form? How does this material like get crystallized in a solution? So I would like to show you a small movie where you can clearly get how this material start forming. So in a solution, these organic linkers start approaching to the metal centers and start forming the coordination bonds. And with time, they start growing into three dimension. They start growing their molecular weight, but while growing, they put some pores inside, which are perfectly ordered pores. So we exactly know that where are pores and where are not. And once its molecular weight grows up, then these materials form beautiful single crystalline materials, which can be just characterized by the single crystal X-ray diffraction analysis. And in these cases, as I said earlier, you can put different functionalities on the linker. You can change different metals. You can change the size of the linker to have the materials with different pore size, as well as we can have various solvents inside, which can do the type of catalysis or type of adsorption studies. And since these materials are very beautiful crystalline material, they can be characterized very well. There is no doubt about their structural features, and that is why these materials can be applied for very much into different applications. So in these cases, metal organic frameworks, as I said earlier, they have permanent porosity. They have we can determine that what these materials could be. They have structural rigidity, and you can change a metal and you can get the structural diversity. They are very reactive because now you can do different chemistry on the metal nodes as well as organic linkers, and you can even do the metal exchange. You can replace one metal with the other, and this is the in this way you can actually tune the properties of materials for different application. And for that reason only, these materials have applied for the sensing, carbon capture and sequestration, chemical separation, renewable energy devices, and removal of the different toxic pollutants and capture. And the important factor over here is that materials can be synthesized on the demand of the application by tuning and fine tuning of the optimization of the properties, which could be important for multiple applications. But as I said earlier, so these materials are purely organic materials, and these materials can be, these materials are purely inorganic, organic materials where there is a hybrid juncture in between, where inorganic metals coordinated to the organic components, giving the metal organic frameworks. But does any one of you has ever wondered that if it is possible between coordination of the metals with organic linkers and giving out the framework, but is it possible that covalently attach different molecules to give the framework? And for example, in 1916, Lewis theory gave us that 6 atoms of carbon, for example, 2 atoms of boron, 4 atoms of oxygen, and 8 atoms of hydrogen can be assembled together in a molecule where these electrons of each atom can be shared, forming a covalent bond. This was the first theory which has given a clear structure about the bonding in these materials. So it was showed that from atoms you can form the molecules, but from molecules can we form the frameworks which are definite, which are crystalline, and we exactly know that what kind of packing these materials have. Is it possible? So this was the question which was being asked in multiple years, that can we have the framework which are completely organic, but these materials are crystalline, they have order, and they are precise in their dimensions. They have long range ordering as well. But this question has never been answered until very recent ones. So what happens in general when we think about any applications, any synthesis reaction? For example, take an example of this tetrakis 4-bromophenylmethane. When they start cross coupling using Yamamoto coupling reaction, they will give you the material. Material will be highly porous, like surface area could be like, okay, 7,100 meters square per gram. But ultimately, these material are not the ordered materials. And what I mean by order means these material have various pore size. These material could be microporous, mesoporous, and pore size could be various size, because there is no order at all. And as compared in the PX study patterns, you can see that there is no particular PX study pattern showing that what is kind of material these are. So practically speaking, if these materials start growing into 3-dimensional in a particular order, these materials should have a structure like this, and which should have a powder PX study pattern like this. But it is never happens, because now we are not giving the proper conditions to crystallize these materials in a particular fashion. And to do that, we need to give some definite synthetic conditions, which was not provided here. And as a result, we saw that, okay, these materials are just amorphous material. There is no particular order. But at that point, everybody started thinking that, can we think of different approaches to synthesize these materials in a particular order? But what happens? For example, there are several membrane filters. For example, all of you have these ROs in our home. There are some membranes which are made from the polymers, which are made from these kind of materials called PIMs, which have microporosity inside. There are some of the materials which are synthesized by Suzuki coupling, Yamamoto coupling, and various cross-coupling reaction, which forms networks and microporous polymers. And these materials, when they form the polymers, they leave the porosity inside. But these are all amorphous materials. There is no definite order. And what I mean by order exactly, here I can show you exactly. These are white colored are the carbon atoms, red colored are the oxygen atoms, and yellow ones are the boron atoms. So now, are there any materials, can we synthesize any materials which have definite order in there, which have definite crystallinity in there? So that means when these materials form, they should have a definite structure in there. They should have, like, we should know that, okay, this is one atom, other atom would be exactly at this particular position. And that is why crystallinity do. So can we impart the crystallinity in these microporous organic polymers? There is no metal at all. These are just composed of carbon, nitrogen, oxygen, sulfur, and boron. Very light elements. And this could have different applications because they are very light as well. But there has to be crystallinity. So how can we do that? So many of you are organic chemists here. So there are so many reactions which are reversible in nature. For example, if you take any reaction where 2 organic components which have different topologies can react with each other, forming oligomers. Oligomers, small components which have very tiny fragments. But there are so many defects in there which forms bigger oligomers. But these materials are same as the microporous polymers which I have spoken in 5 minutes earlier. So how can we create these materials error-free, and then we can call these as a covalent organic frameworks without any defects inside? So to do that, we have to use different reactions which are reversible. what reversibility can do, for example, there are a lot many errors in this material. They can be corrected after going back and forth. So if there is an error, this molecule can be detached away, go back to the original state, and then come back and put it into exactly where it has to be, and then form bigger oligomers before it forms perfectly crystalline order crystalline materials which have high thermal and chemical stability as well. So it is possible, if you put per specific reaction condition, it would be possible to synthesize the materials which have perfect order in their backbone. And to do that, in 2005, the group of Professor Yagi in California, University of California, they thought that, okay, then we can assemble different organic linkers which have C2 symmetric, or two organic linkers which are C3 symmetric, or one C3 and one C2 linker. We should ultimately get materials which are which should have the which should show the crystallinity as well as some.
Dr. Pradip, are you facing some noise?
I'm getting someone's sign. Yadav, Dasharath.
Yeah, sir, I have done it. You can go ahead. Sorry for it.
Okay. So in these cases, when three C3 symmetric linkers, two C3 plus C3 linkers, and one C2 plus C2 linkers can be assembled together, forming honeycomb kind of structures in there. So how can we do that? So now we come back to the organic synthetic conditions, where we all of us know that boronate boroxine anhydride formation reaction, where three boronic acid can come together forming such kind of monomer, and there could be release of three water molecules which can drive this reaction back and forth, forming the perfectly crystalline as well as the materials with high porosity. So how can we go ahead? Now three C2 symmetric linkers, there are two boronic acid groups which we need to give a definite synthetic condition, and this should have a framework now. Organic linkers forming the frameworks, which was never been possible before 2005, before this group first time published a paper in there. And can we extend this reaction into other materials as well? Yes. When we start reacting boronic acid with different materials such as HST, we can start seeing the triboron ester formation, and which we can finally see the materials into three-dimensional material, which we can see the formation of, which we can see the formation of different COFs such as COF5. So using different organic linkers and different organic reaction, it is possible to synthesize the different covalent organic frameworks which are porous, which are crystalline too. And in a way, when it comes to the synthesis and structure of these materials, it is possible to detect the ultimate structure of these materials. For example, these are the PXRD, powder XRD patterns, which in a last case where I showed that these materials are completely amorphous. But when you form the covalent organic framework, these materials are very high crystallinity, and now we exactly know that what kind of pores, what kind of structure these materials have. And we can simulate the structure using Material Studio and determine exact structure of this material. And we can compare. Now these materials are not single crystalline, but these are the powder XRD, powderous material, which more or less look like this. And we can determine the structure in a software called Material Studio. You can then, using the computer simulation, you can determine the powder XRD of this particular material and compare with your PXRD material, PXRD of your material, which you have got in experimental way, and check that what is the difference in these materials. And this can even be characterized further by FTIR as well as the 13C carbon NMR analysis. And this was the case for COP1, where it was seen that these materials have the crystalline eclipse structure. And what I mean by eclipse are these layers are not stacked on top of each other, but there is a big deformation, and that's why we see the staggered combination of these materials. But in this particular case, what we see in general is what we see in general is these materials are perfectly staggered, and they have high crystallinity in their backbone as well. So, and someone might ask that, is it possible to synthesize single crystalline material like MOFs? Yes. In three-dimensional material, it has recently been shown that these materials can be synthesized in single crystalline, and using a single crystal XRD analysis, you can even characterize them very well with all the precise atomic positions. So now I will just show you that, as I said in the metal organic frameworks, now this tetraamine linker can start coordinating with different dialdehyde molecules. And now this is a common ship-based reaction which we do in the lab every day. And in this case, now we know that, okay, where exactly nitrogen should be sitting. Okay, exactly over here, there is a nitrogen. There is a other linker which is coming from here. So this is the advantage of crystalline material. These are really a smart material because you can predict the properties of material by using different organic molecules. We can induce something inside. For example, I can put any fluorine molecule, any molecule here, and I know where exactly this molecule would be sitting. Even more interestingly, this material when this reaction, ship-based reaction happens, there are some water molecules which are leave out in the reaction. So now we can predict that these water molecules can be sitting in the pores, and which were seen in the single crystallic study analysis of these materials. So this way we can predict the properties of materials, as well as we know where exactly these materials can be applied. So in this way, not only boronic acid trimerization reaction or boron ester formation reaction, but different reaction. For example, in our lab, we have used different cyano-linkers forming covalent triazine frameworks. As I showed earlier, ship-based reaction was used. There were different reactions such as polyimide reaction, hydrogen forming reaction, and very recently we have even shown the cyanovinyl reaction for the synthesis of covalent frameworks. And what is the beauty of this material is that they have unlimited chemical tunability, because you change one of the linker and you get completely different material with completely different properties, which is really interesting because as per your choice, you can tune the properties of materials. You can get a completely new material just by changing one linker over here. Second, they are crystalline. As I said, now I know that, okay, there is one layer over here, there is other layer in there. How big are the pores? I exactly know the ordering of the material. I exactly know where are the atoms placed. So this is crystallinity, what it does. Rigid architecture. These materials have the very, very rigid architecture. They are porous. And now once you synthesize the material, these layers can stay there forever. So which is really good because now there is a rigidity inside. They are having low density because there are just atoms as a carbon, nitrogen, oxygen, and boron, which can form these particular materials. And they have high permanent porosity because pores such as 2 nanometer, which would give a surface area as high as 5,000 meters square per gram, which is very good for the adsorption, hydrogen storage, so on and so forth. And most importantly, since these materials, for example, in this case, there is there is not a single bond which can be hydrolyzed using acid or bases, and that's why these materials have very stable as well as they are robust too. And due to these particular properties, these materials have been applied for the multiple applications. For example, gas storage, we can store the hydrogen, which can be used for the fuel cell. They have been used for the separation. You can have the dyes, which generally come out of many industries, and you can pass it through the COF membrane. And now you see that, okay, just pure water is coming out, leaving out the dyes on the top. So these materials can be used for the chiral separation as well. Then these materials can be even used for the chiral catalysis or chiral separation as well. You can load some metals like graphene, and you can have the catalysis of any type of materials. You can use this material for the proton conducting in the fuel cell. These materials can be even applied for multiple applications, including the optoelectronics as well as batteries as well as supercapacitor as well. And most important factor, when I joined in the TU Berlin in 2016, first question came, since these materials have the porosity and rigidity, they should show the rapid diffusion of the charges, as well as they should show the high interaction with the surface, because now you have big pores. I can put any electrolytes, which people working in the electrocatalysis and other applications like battery and supercapacitor, they must be knowing that how important porosity is in this application. And which is very, very important, that once I put any moiety inside, then they can stay there forever without forming the dimers, which generally stops the reaction among these materials. And they actually, people working in the homogeneous catalysis know the pain of forming the dimers, because as soon as these materials start from the dimers, they stop reacting with each other. There is no activity at all for the catalysis. But in these materials, once you put any moiety inside, this can go for working for hours and hours and hours. And in this respect, these materials are very, very nice. But these properties are very nice for one particular application, which is called as a photocatalysis. So how would you see that in photocatalysis? And particularly when I talk about the photocatalytic water splitting, where you can use the solar energy, where catalyst absorb the light, and it can split the water into pure hydrogen and pure oxygen in presence of co-catalyst, or in presence or in absence of the co-catalyst, giving out pure hydrogen, pure oxygen. And as all of us know, on Earth crust, there is almost 71% of the water. If we can split the water into hydrogen, we can tomorrow solve all the problems with the petrol and diesel, which are increasing each day with the prices as well. So we need a material which can do that kind of catalysis as well. I will not talk about some of the materials like TiO2, which is known from the years, but the only problem with TiO2 is they absorb in the UV light region. But we cannot provide the UV light when I go outside the atmosphere or in the normal atmospheric condition. So we need to have the material which absorb in the visible light region, visible light in a normal sunlight. So to do that, organic materials are very important because they can be tuned according to our own choice. So where exactly this field is going? In carbon nitride, in 2009, in our group, we have first time showed that carbon nitride, which are completely organic material, can do the photocatalysis, which are semi-crystalline material and which can catalyze the water splitting very, very efficiently. There are covalent triazine frameworks, different linear polymers and porous polymers, which can do this job. But what is happening with the covalent organic frameworks? Are these materials usable for this application? Till the point we were working, there were just a couple of reports where it was being shown that covalent triazine frameworks made from triazine moieties, as well as the covalent organic frameworks which are generated from the triazine in their backbone, can be used for the photocatalytic water splitting. But this field was not going anywhere beyond that. But while starting working, what I found was we can incorporate some of the diacetylene moieties which have good applications into hole or charge transfer properties, or some photocatalysis properties such as dye degradation. So a small moiety, which is diacetylene moiety, can do a lot of changes in the structure and properties of the materials, showing the really, really good photocatalysis. But is it possible to incorporate such a targeted moieties into the covalent organic frameworks to do the photocatalysis? And this was the target which we took, and then we started thinking about how can we do that. For doing that, we have installed this diacetylene moiety in a diamine molecule, as I showed earlier. And we have also installed the acetylene moieties in another diamine molecule. We started reacting these materials with 1,3,5-triformine fluoroglycinol, which is a trial end now. When we started reacting these materials with each other, we got the materials which should ideally have the structure like this. This is a structure which we generally expect in these cases, but in a way, this should be crystalline. And so by using 1,4-dioxane acetic acid as a catalyst and 120 degrees Celsius 72 hours, we could synthesize materials which should have ideally structured something like this one. So now, if we get a material out of these two components, this should have the exact structure what I showed it here. And it should have a pore size of 3.4 nanometer. The other acetylene-based material should have the pore size of 3 nanometer. And these materials should have a crystallinity as well. And for the first time, what we did was we did the powder excited analysis. And here we can see that now these materials have definite peaks, which show that these are the crystalline materials. And we compared the PXRD patterns of these materials with the simulated structure using Material Studio. And we compared difference among these two patterns. And what we saw that there is not much difference than what we synthesized and what we predicted. So from this one, we could say that, okay, materials, whatever we have synthesized have more or less similar structure like this, with pore size of 3 nanometer for the acetylene-based COF and 3.4 nanometer for the diacetylene-based COF. But what about the porosity of these materials? Because COF should have the porosity, otherwise there is no point of application of these materials for any application, any photocatalysis application. We did the surface area analysis. Now we can see the nitrogen uptake on y-axis, relative pressure on x-axis, and you see the adsorption of the nitrogen in a particular way. So from this analysis, we could say that the COF, BDDA COF having diacetylene moieties have the surface area of 756 meters square per gram, and TP EDDA have the surface area of 523 meters square per gram as expected because it has smaller pore size. Not only that, but I'm just introducing you different methods to characterize different materials as well. For example, in this case, we have finalized the surface area using adsorption analysis. Now, how do we know that whether these moieties, acetylene, diacetylene, is there any imine linkage inside? We can do the 13C NMR analysis in a solid state. And here, what we found that using 13C, we can definitely see that there is a presence of diacetylene moieties. The peaks representing are present. There are acetylene moieties exactly at this particular location where we expect and simulate, and different linkages. For example, imine bond is still intact, and every moiety which we are expected is still there. We have even used the FTIR analysis to determine different functionalities in these materials, and we could definitely say that, okay, now we have material which have crystallinity, which have porosity, as well as it have definite moieties like acetylene and diacetylene in its backbone. So now we have characterized the material. So next target was, since we have material which have some structure like this, there are diacetylene and acetylene moieties inside. Can we apply this material for the photocatalytic hydrogen generation? You take a water, and can we generate hydrogen and oxygen in these materials? So this was the biggest question what we were supposed to answer. And to do that, and for the pair comparison, what we thought, we have a COF which have TP-EDDA with acetylene. We have another COF where there is a diacetylene. But there are some nitrogen atoms which can hamper on the photocatalytic hydrogen generation. And to make a pair comparison, what we did was, we have even synthesized a just phenyl-based COF without any acetylene and diacetylene moieties. So now we have 3 different COFs. Getting interesting, like acetylene, diacetylene, and only phenyl. And to do that, we have followed exact same conditions as I showed earlier for these 2 COFs, and we got the material which was crystalline, which was even more porous as compared to other 2 counterparts. And so now it's our target that we had 3 COFs where there is a diacetylene moiety, there is acetylene moiety, and there are just phenyl moieties in their backbone. So what first characterization any person who is working in this area would do is UV analysis and solid-state UV analysis, where we can exactly see that how these materials are absorbing in the visible light region. So to do that, we did the solid-state analysis, and this is how this material look in general. Very beautiful powderous material with distinct colors, which can be distinct from its appearance itself. And to do that, we did the solid-state UV analysis, and now you can see that the COF TP-BDDA have the absorption. This green line represents the absorption of this particular BDDA COF, and now we can exactly see that COF having diacetylene moiety in its backbone shows the absorption more in the visible region. So it is becoming more and more interesting now, because you just put one moiety inside and you start absorbing the materials more in the visible region, as we are expecting now, because it is really important for us to get the material absorbing the visible region to achieve the photocatalytic hydrogen generation in just normal sunlight. And what we observed was the other 2 materials, for example, TP-EDDA having the acetylene moieties, and the TP-DTP having phenyl moieties, absorb more in the UV light region, which was expected because their band gaps were pretty higher as compared to the TP-BDDA having the diacetylene moiety. So now it was the testing time for us. We did everything. We have a material which has porosity, crystallinity, absorbs in the visible light region, but can we see the photocatalytic hydrogen generation in this material? So in our lab, we have made our own setup wherein we can put the catalyst inside and do the inline analysis. And for doing this, we had a quartz reactor, which was kept 10 meters apart from the xenon lamp, having the intensity beyond 395 nanometer. And then in this particular reactor, where there you can clearly see the magnetic needle, we had a 10 milligram of the catalyst, 20 ml of the water and TUA solution in 9:1 proportion. We had 3 weight % of platinum as a co-catalyst. And in this particular reaction, TUA acts as a sacrificial electron donor, because we don't want to get the oxygen in there, because it is a 4 electron process, which is really hard to achieve. And we were just concentrating on the hydrogen generation rather than the oxygen part of this particular reaction. And then we mixed everything together, evacuated this particular gas chamber with argon multiple times, removed oxygen from it, and started the reaction shining with this xenon lamp. And what we observed, most interestingly, here we can see that hydrogen evolution rate over here on the y-axis, and the x-axis shows the time. And now you see that TP-BDDA COF having the diacetylene moieties shows the highest hydrogen uptake as compared to other 2 counterparts. And mainly the reason could be these COFs have diacetylene moieties in their backbone, they have lowest band gap, and it absorbs in the visible region. And as compared to TP-BDDA having diacetylene COFs, the acetylene-based COF and the phenyl-based COF show very negligible hydrogen generation. So there is a distinct difference happening because of just one small moiety, which can change all the scenario for photocatalytic water splitting. And in this way, we could achieve the efficient photocatalytic hydrogen generation. But someone of you might just say that, how do you know that this hydrogen whatever is coming out not from the catalyst? Obvious question, because everyone will think that, okay, your catalyst is degrading in water and TUA and during the platinum and during the light. Yeah, we consider that possibility as well. We did the labeling experiment. In place of water, we added D2 in there. And now we saw that, okay, there is just exclusive generation of D2, confirming that whatever hydrogen is coming, that is exactly from the water and not from the catalyst. There is no corrosion of the catalyst at all. So the important question is that, okay, is that all your, does all of your materials are doing the catalyst till 10 hours? No, this material can do the catalysis for more than 60 hours continuously. So we chosen the diacetylene COF since it was showing highly efficient hydrogen generation with a rate of 325 micromole per hour per gram of the catalyst. We used this COF and started doing the photocatalytic hydrogen splitting experiment. We did it for 80 hours. So now what we have to do, we have to start the reaction with the time and observe how much hydrogen is coming out. And then what we saw was with increasing time for 20 hours, there is no drop in the hydrogen generation and after 20 hours, we see that there is a TUA which is getting exhausted, and we have to add a new alicot of TUA, and then it starts generating hydrogen with the same rate. So by using this particular COF, but we showed that by adding some moieties in the backbone of this particular covalent organic frameworks, which we can do the photocatalytic water splitting, just hydrogen from water, which is really, really important as a fuel. And in this whole process, we could even show the durability for 80 hours. That means once you add the catalyst for 4 days, you can just continuously see there is a hydrogen generation, which is pretty important and pretty impressive as well. But as I said earlier, there was always a question about the stability of these materials because these are composed of the imine. But how can we overcome that? To do that, we have chosen the non-homogeneous condensation reaction, where we have seen that using non-homogeneous condensation reaction and taking the advantage of active CH2 groups in these kind of particular linkers, we can synthesize the COFs which are composed of just carbon-carbon double bonds. And there is no bond which is labile now, which cannot be reacted during this whole process. And most importantly, these materials showed the improve the photocatalysis and energy storage properties as compared to the other counterparts like imine-based COF as well as boronic acid COF, which is pretty important and which is pretty nice as well. But we thought the people working in organic chemistry might know that these cyano groups are always been considered as labile groups. We can click those materials, we can convert them into the tetrazole, triazole, and we can even get these materials into acidic group as soon as you put into acid and base. So which is not good for any catalyst, because now you are not having the material which you expected. You are having the material which is something different than that one. So we thought rather than this asymmetrical carbon-carbon bond where cyano groups are there, can we have the material which could be more or less similar to like polyphenylene vinylene, which is known in the hundreds of the years earlier, and which have different applications in LEDs as well as solar cell as well. Because now there is no bond, there is no asymmetrical bond in between. These materials have high electrical conductivity, as well as they have very good electroluminescence, and they have some magnetic properties as well, just because of the symmetrical bond. So we thought, okay, it will be interesting to have the materials, we have these symmetrical CC bonds, and we can incorporate some of the triazine moieties which are a part of covalent triazine frameworks or carbon nitride or some of the polyimide networks as well. And these are the moieties which are really important. And to incorporate that, we thought that, okay, we can have a molecule, trimethyl triazine, where this nitrogen poor nature, the electron poor nature of nitrogen can remove the electron density from here and start activating these carbon atoms. So to confirm that one, we have reacted this particular trimethyl triazine with benzaldehyde in methanol and using methanol as a solvent and NaOH as the catalyst. And what we found that we can get this kind of molecule. And what happens in general in presence of base, one of the proton can be abstracted by base forming the carbanion. And this carbanion starts reacting with the benzaldehyde. And this is a typical aldol condensation reaction in presence of base or acid. So by using such a small molecule, you can synthesize the monomer, which can be extended into 3 dimensions. So how can we do that? This is really important. Like, okay, just a small molecule can be extended into 3 dimensions. And here, trimethyl triazine, having this active CH3 group, was converted into the framework by reacting with the terephthaldehyde or C3 symmetric 135 formyl benzene. So which is important for any particular application. And now this material, for example, here you see that these are the triazine moieties coordinated to the phenyl ring to just carbon-carbon double bond, very similar to the PPV, what I showed in the previous slide. And these materials are very much good crystallinity. They are exactly matching their PXRD pattern with similar pattern. They have pore size of 1.9 nanometer, which is pretty nice for any applications. So someone might ask that, okay, what is happening with the porosity of this material? These materials have very high surface area, and they have shown surface area beyond 1500 meters square per gram. That means 1 gram of the material have the surface area as high as 1 tennis court, which is pretty impressive to do any kind of chemistry inside. And Most importantly, even this triazine-based based COF has even showed the absorption in visible light. And when applied for the photocatalytic hydrogen generation, this material even showed the efficient hydrogen generation. So just taking the advantage of high crystallinity, porosity, and presence of the triazine moieties in this COF, we have showed the utilization of this COF for the photocatalytic hydrogen generation, which is really a smart material, and we can do the different catalysis to generate the hydrogen, which can be later used as a fuel using the fuel cell cars. Lastly, not only photocatalysis, but we have deposited some of the materials like metals on top of this graphene, like graphene on covalent organic frameworks, and did some of the organic transformation reaction, as well as we have incorporated some of the bipyridine moieties, coordinated different metals, and did the oxygen evolution reaction. And very recently, we have even had a wonderful result where we have showed the radical polymerization using covalent organic frameworks. If someone is interested, please browse through the publications below here. And with this, I would like to summarize. I hope I have convinced that by applying reversible reaction, crystalline and porous COFs can be prepared, which are next generation smart materials. I believe just by incorporating the diacetylene-based moieties in COF backbone, we have showed the efficient photocatalytic hydrogen generation, which just shows the hydrogen generation from water, which is pretty impressive. And lastly, vanillin linked COFs, which are synthesized using trimethyl triazine, a very tiny, very fantastic molecule. We can synthesize the COF, which are fully conjugated, and these materials show the promise for the photocatalysis. Without mentioning that, I cannot end the presentation. I would like to thank my professor Arne Thomas, who is supporting all of these activities, and our secretary, my colleague, which are more or less visible in this particular photo. This is a picture from our group trip last year, and I would like to thank for the support of analysis. I would like to thank Alexander von Humboldt Foundation for the support of my fellowship in first 2 years, and now UniSysCat for the fellowship currently, and TU Berlin for all the support. And lastly, thank you all for your attention. I will be happy to take any questions.
Hello. Thank you. Thank you, Dr. Pradip sir, for your scholarly talk. Now the session is open for discussion. If the participants have some queries, doubts in their mind, or questions to ask to you, they are now open to ask the question.
Sir, I have one question.
Please,
Pachfule, sir. Do you hear me, sir?
Yeah.
Yeah, sir, it was very nice, interesting, very much thank you for this. But I have many questions, but just I would like to ask 2 questions.
Yeah.
As far as disorder into order form you talked about, what about stability of that material?
This is an excellent question, and we always see this question every time we deal with these materials. Of course, this is a fantastic question. I would expect and then about the stability. For example, boronic acid COFs, which were the first COFs synthesized in this whole process, they were really unstable. The first part of my presentation where I showed that boronic acid trimerization. As soon as you put this material on the room temperature in the normal synthetic condition, they start forming the polymers and degrade. But when it comes to the UV-based COF, where I showed the photocatalytic water splitting, these materials are really stable. You can put it on the atmospheric condition for weeks. And most importantly, when it comes to the last part of my presentation, where we have showed the CC bonded COFs, we have kept this material on the table for 6 months, and nothing happened to this material. So it is this is a systematic evolution. Boronic acid was really unstable. Imines were having considerable stability, but the current COFs with olefin linkages as well as the cyanovinyl are very stable. And this is about the stability in atmosphere, but chemically also these are stable COFs.
Okay, thank you. And one more question regarding hydrogen gas storage. Hello, sir.
Yes, sir.
Regarding hydrogen gas storage, is it safe for transportation and so on?
Actually, this question has already been addressed by many scientific community in there, because if you know that the best example I would say, when you travel to Agra anytime to watch the Taj Mahal, all of these buses are made from the hydrogen storage fuel cell buses, where hydrogen is stored in And interestingly, I started my presentation with these carbon nanotubes, and the cylinders which are made from carbon nanotube, just completely from the carbon nanotube and composite from the polymer, this gas can be stored under high pressure. And what we are trying now, when I was working the MOFs, when I was doing my PhD in Pune, we were working on the synthesis of the MOFs, which can be filled in these tanks and absorb more and more hydrogen, store more and more hydrogen. So this was our target at that point, which we couldn't achieve what we expected, but it is possible to store and it is safe. Of course, like for example, in Germany, there are, I think, almost 22 points where you can store the hydrogen. And if if any one of you know, there is a Toyota Mirai. There is a vehicle named Toyota Mirai. Just this is completely based on the fuel cell, and you have to store the hydrogen in there.
Okay.
Okay. Thank you, Pradip sir. I'm
Thank you,
very
sir.
happy.
Thank you. Very nice answers, sir.
I'm very happy to let you know, Pradip sir, that just I received information from the host, Dr. Kosti, that 1.2K, that means 1200 plus participants on YouTube and 100 participants on Zoom have been benefited by your live talk, sir. And they have shared
Hats off.
they have shared many.
To all of your organization. I am just giving my research talk here.
And they have shared many praiseworthy remarks for you in the chat box also. If there are some questions in the chat box of YouTube, I hand over to Dr. Kosti sir. He will read out the questions and you may satisfy them. Please, over to you, Dr. Kosti sir.
Thank you, Lokde sir. First of all, I congratulate to the Dr. Pradip Pachfule sir. Very excellent talk, sir. Very excellent. I know the way of you are presenting, but after I think 2 to 3 years, I'm just looking now. Very impressive, and so on. We will talk maybe later on. But right now, there are a lot of appreciation coming in Zoom app, Zoom chat, as well as YouTube live stream. So I took only 2 messages and 2 questions. So I will read some questions. One question is Dr. Suman Pawar, and the same question asked from Banerjee AS from University Delhi.
Okay.
They are asking that, is this material eco-friendly and biodegradable? What is your...
So apparently, if you see that if material is just made from carbon, nitrogen, oxygen,
okay,
like which is more or less component of every cellulose, which our body is made of, you know, like kind of very much cellulosic materials, and we generally eat cellulosic material. I don't recommend to eat the COFs directly, but I don't think, since material is just made from carbon, nitrogen, oxygen, and sulfur, I don't think it would be have any impact on the atmosphere or, you know, current nature. But most importantly, I would even go one step ahead and say that even these materials have been applied as in bioimaging as well. You just exfoliate some of the layers and do some of the compatible bioanalysis inside these materials, or use this material. For example, if I remember well, there was a material which was exfoliated into small thin layers, and now they tagged these materials with some of the different fluorescent materials, and they use this one to treat cancer, I suppose, if I remember well. But yeah, these are biocompatible material. There is no problem at all.
Thank you, sir. Another question from UK, England, who is Murkad. He's asking that in your inorganic MOF and organic COF, the difference is that the porous size, it's a varied, means in organic COF, he's understand that pore size is constant, but in inorganic MOF, the pore size is varied. So how it is a benefit to the application, and how it will be applicable?
So actually, if I understood the question, what he want to say is, in MOFs you can tune the pore size. For example, you can terephthalate layer with biphenyl, even more towards the high pore. But it is even possible in the COFs as well. You change one linker. For example, if I remember well, I showed a slide where we had showed the acetylene and diacetylene. Okay. So acetylene was having pore size of 3 nanometer and diacetylene was having the pore size of 3.4 nanometer. So it is possible to tune the pore size. You can even go further. Like the last part of that particular section was acetylene, diacetylene, and terphenylene. So now we can tune the pore size. Like, okay, first one was having 3 nanometer, second one was having 3.4 nanometer, and the terphenylene COF was having the pore size of 4 nanometer. So you can tune the pore size as exactly as same what we was doing in the MOF. But I agree with one opinion. It was very easy in the MOFs because material react in a single crystalline way. So you know exactly, okay, what is happening. There are some issues in this covalent organic framework, but as I showed in my last part of presentation, nowadays even COFs are getting analyzed using single crystal excited and single crystals as well. So ideally, I won't compare these two materials, but yeah, whatever you can do in the MOFs, it is possible in the COFs as well.
Thank you so much. The last question from Dr. Varsha Sawant, who is an assistant professor of YCI Satara. She is asking that whether these molecules are stable in light as they are being used as a photocatalyst in visible region.
Absolutely fantastic question again. So I would say that, okay, generally what happens, like, you know, you shine material with some light and then they start reacting differently. Because what happens, for example, just take an example of what you have one COF which have styrene, like, you know, C11C in there, and there is another layer of the COF which have the similar kind of bonding, and they start reacting with each other in the 2+2 cycloaddition, which is a textbook chemistry what we see. But what happens is that in some of the materials where there is bond is there, it may be possible to see this 2+2 cycloaddition reaction. But when it comes to the CN, it is not possible to form the 2+2 cycloaddition reaction. And most interestingly, we use this acetylene and diacetylene COFs, which might form 2+2 cycloaddition. But to do this one, we bombarded our materials in UV light for 2 hours. But still what we saw that there is no at all formation of the linkages in between the layers or 2+2 cycloaddition in material. And answering the question of what happens during the photocatalysis, yes, they start degrading a bit. But if you take a hydrogen from water for 5 days, you expect that much, I suppose.
Okay, thank you so much, sir. There are a lot of questions, but what I will do, I will send to you. I will take your audio or written answer, and I will share with who asked the question, because time limit we have, and we cannot cover all the questions. But thank you so much, Dr. Pradip Pachfule.
I really enjoyed. Thank you all of you again. It was wonderful organization, and then I'm seeing that, you know, how we are moving ahead with the different time. Excellent organization. Thanks all of you again. I really enjoyed the session.
Thank you, sir. Thank
you so
Thank
much.
you, sir. Dear Pradip, sir. Hello.
Yeah.
Dear Pradip, sir, in spite of your busy schedule, you have spared time for us.
On behalf
of Department of Chemistry and Internal Quality Assurance Cell of DP Bhosle College, Koregaon, I extend my sincere thanks towards you for giving such a scholarly talk and satisfying the queries, questions, doubts raised by the participants. Again, thank you, sir, for providing us an opportunity to organize such an international webinar in collaboration with Technical University Berlin, Germany. Thank you very much, sir. Thank you.
Thank you. Have a nice day to all of you.
Thank you, sir. Have a nice time, sir. Now, dear participants, session second will begin with the introduction of the resource person, Honorable Dr. Deepkumar Joshi, sir. And for that purpose, I invite Dr. V.S. Kosti, Assistant Professor, Department of Chemistry, DP Bhosle College, Koregaon, to introduce the second resource person, Honorable Deepkumar, sir. Over to you, sir, Dr. Kosti.
Thank you, sir. Thank you so much, sir. I warmly good afternoon to all guys. We are moving to second resource person, who is well known, Dr. Deepkumar Joshi. He is assistant professor in Sheth M Science College, Patan, Gujrat. He is a very excellent teacher. Personally, I learned a lot of things from him. He completed his PhD in age of 27. It is a very impressive, sir. And he got a prestigious Inspire Fellowship from DST India. Deepkumar is awarded with the Best PhD Thesis in 2014 and Best Undergraduate Teacher Award in 2019 by Gujrat Science Academy. He has published more than 23 papers in reputed journals and has been serving as a senior advisor for an International Journal of Chemical Studies. He has guided more than 30 MSc students and currently is doing so. Now, I request to Dr. Deepkumar Joshi for a session. Over to
Thank you,
you,
sir.
Dr. Deepkumar Joshi. Yes, sir.
Thank you, sir.
Yeah. Yeah. You are
Am I
visible,
audible,
sir.
sir?
Yes, sir. You are audible. You are visible too.
A very good afternoon to one and all. I am really thankful to the organizers for giving me this opportunity and be with you all during this pandemic. And we will be discussing very basic topics on how to identify these smart materials and how we can correlate this technique with the technology. So I'm just sharing the presentation, and once I share the presentation, I'll just start up with the same. I would just request Dr. Kosti that once the presentation is visible, just let me know, sir.
Sure, sure, sir.
Yes, sir, I have shared. Is it visible?
Yes, sir. It is
Yes,
visible,
yes.
sir.
Go ahead.
It is visible.
Yeah. So friends, I'll just take this opportunity and try to correlate the various chromatographic technique and how this technique has turned into technology for detecting different materials. So let us begin so that we can see the most important things. If you see, science seems transferring technique into technology. Let it be the precipitation methods, the distillation methods, the extraction methods. These methods, whenever started with, it all started with basic concepts in science as well as very reasonable techniques. But today this has jumped into a technology in the petroleum industry, in the pharma industry, in the drug industry, as well as in the food industries. So we are just going to focus on one of the growing demands that has come out in the last 50 years regarding chromatography. Since the inception of chromatography, the technique today has turned into technology where you had HPLC, GC, HPTLC, TLC, and many other demanding technology today. So my main focus would be around first making a very short discussion followed by a mechanistic video on each of this technique and then correlating them with each technology so that we can just correlate with the title and justify the title and the theme of the conference. We all know regarding the stationary phase, mobile phase, and retardation factor, the three very popular terms in chromatography, along with its strategy of separating components physically prior to examination. So I'll just start with an animated video regarding the historical development of chromatography. Nevertheless, do not mind regarding the voice of the video because I'll be continuously explaining the video also. If the voice of the video is not that much audible, do not worry at all. If you see that the historical development of chromatography started with the very first invention by the Russian botanist Mikhail Svet, where he separated the plant pigments in 1906. The main aim was to identify the number of components that were present in the leaf extract, and now there is a very good animated video which can be helpful to just recognize what was happening in this first ever flagship experiment that led to the invention of the technique chromatography. You can see a mixture that is being placed on the top of this column, which is filled with calcium carbonate, a material that is used to separate, and now it is filled with an excessive amount of mobile phase so that it can gradually travel downwards. And you can see as the time will pass, the things will travel from the top end of the column towards the bottom end of the column. The compounds are literally getting separated. Once they are separated, you can just remove it out very smoothly. you can separate out individual fragments of the separated components, rather to say in this experiment, the plant pigments. So this is where everything started in chromatography, where the compounds were recovered. So this was that very first experiment from where this chromatography started, with the justification to its name, that was chromatus and graphene, indicating colors and to write. Now it was our chance just to discover these two words, that was stationary phase and mobile phase. And before we move on with the discussion regarding the same, the increment went on with the invention for the other chromatographic technique, where partition was the main mechanism. Martin and Sinch were awarded the Nobel Prize for their gas liquid chromatography instrumentation. For the very first time, they came up with the idea of partition chromatography, and a total new era of separation chromatography came into existence. According to IUPAC, this is a very brief definition we have for chromatography, where it is a physical method of separation with the components to be separated and distributed between the two phases, that is the stationary phase and the mobile phase. We all know regarding the stationary phase, they can be solid, they can be liquid coated on a solid support, but astonishingly, you have the immobilized polymers and the surface bonded shorter chemical species that can also be used today as stationary phases. As well as gas are the mobile phase, along with supercritical fluid mobile phase that are used today, which is one of the most benefited technology by the blend of both liquid chromatography and the gas chromatography. Now we are directly coming to the point from where we will be relating each technique, each mechanism to a technology. We are just going to identify these 5 to 6 different techniques, these mechanisms, which are fundamentally based on separation, and we'll be moving towards the detailed study of each and indicating the related technology. That can be adsorption, partition, ion exchange, size exclusion, bonded phase, and affinity chromatography. Mechanism of separation, if is identified to be the adsorption chromatography, let us first see what is the technique, what is the mechanism involved, and then move towards the application based on this mechanism that can be used to detect materials. If you see over here, it's an adsorption process and desorption. The white portion is your stationary phase, and these yellow molecules are your analytes, that samples that get adsorbed and desorbed depending upon the flow rate of the mobile phase. This technique, that is adsorption chromatography, is fundamentally based on polarity. And this polarity technique has today been developed to an extent of technology where you come up with gas solid chromatography as well as liquid solid chromatography, that is nothing but HPLC or UPLC. So this is how we can have a correlation between mechanism of separation, that is adsorption chromatography, and its application, that is gas solid chromatography and liquid solid chromatography. Moving towards the second, that is partition chromatography, it will have a different technique, a different mechanism, and this technique or mechanism again will be used for developing and introducing a different technology. Over here, when it is partition chromatography, it is the distribution of the analyte where the mobile phase can be liquid and also the stationary phase can be liquid coated on solid. Over here, before moving towards the technological part of or the application part of partition chromatography, let us make a very thin line clarity that whenever we are talking of the adsorption chromatography, generally we stick towards adsorption phenomena related to solid as a stationary phase. And whenever we are speaking for the partition chromatography, generally we relate the liquid coated on a solid as a stationary phase. So keep these two distinct things in the mind while learning or explaining adsorption chromatography and partition chromatography. And the applications based on partition chromatography resulted into GLC as well as LLC, that is liquid-liquid chromatography. Now this liquid-liquid chromatography is very interesting, where if you see for the first time, whenever we have this liquid-liquid chromatography, the first liquid stands for the mobile phase, whereas the second liquid stands for the liquid coated on the solid stationary phase. So it is a liquid-liquid combination. Such type of explanation is also possible when you are justifying paper chromatography. So these are the explanatory part where you can correlate the technique partition to the applied technology in the physical world. And if you look into the most industries and the research that is being conducted in the organic chemistry, liquid-liquid chromatography and gas-liquid chromatography holds a very high value. Now, moving ahead with the third portion, we have the ion exchange chromatography. This has a lot many applications when it comes to research, when it comes to industry, when it comes to society. We will focus on each parameter. But first of all, let us see the mechanism that is involved in this ion exchange chromatography. Over here, you can see that among the mixture of cations, one of the cation is stuck with the column, whereas the other cation has moved out of the column. It means there is some exchange kind of a thing taking place. And this simple exchange, before we move on for the technology involved, let us check one thing over here. And that is, whenever you have a cation that is to be separated from the mixture, the stationary phase has to be made up of an anion. And similarly, vice versa, when you have the components to be separated from an anionic nature, the stationary phase has to be cation. And the application based on this, if you see the ion exchange resin, that is based on the electrostatic binding, the cation and the anionic exchangers, they have a direct technological application for the softening of the hard water, where calcium and magnesium salts, which pertain to the hardness of the water, are removed by the EDTA exchanger. Even the lanthanoids extraction is being done through this method of ion exchange chromatography. And today, this ion exchange mechanism is very well used in the HPLC technology to separate cations or to separate anions. Before moving ahead, if we talk about this technology to the societal contribution, each and every person involved in the CSIR lab of my state, that is CSMCRI, is constantly working on purification of seawater into drinking water, and they have achieved a lot huge success. And now they are installing these kind of systems, this kind of technology made available from the technique ion exchange chromatography to the people living on the coastal areas, so that this simple technique can help the residents residing in the coastal area to get potable or drinking water from the salty water through this simple technology turned from a technique ion exchange chromatography. So this is how simple techniques developed into a technology can be widely used to help the people, help the researchers, help the society. If we talk about few other chromatography experiments that have today turned into technology based on ion exchange chromatography. It is having a maximum applications in inorganic chemistry, whether it be a lab, whether it be an industry. But if we look into closely, we would identify that these technologies have been developed from very small techniques. And up to this point, up to this junction of discussion, we involved three things: absorption, partition, and ion exchange chromatography. And we had very good applications. Before we move ahead with the further technique turned into technology, one more important part that comes in ion exchange chromatography, apart from hardness of water removal, is much involved in separating out unwanted cations and unwanted anions from other petroleum products, as well as identification of lead, identification of mercury from food products. As we all know that these heavy metals are very much harmful to human body as they are carcinogenics. So friends, this is how simple technique today
Hello, sir. Hello. Can you hear me?
application when it comes to Argos based size exclusion chromatography columns used in the protein purification through this FPLC, that is fast protein liquid chromatography. Friends, if you look over here, this chromatography technique is popularly named by other popular words, that is gel permeation chromatography, gel filtration chromatography, molecule exclusion chromatography. They work on a very simple phenomena, that is stationary phase is a porous gel with a specific pore size. As the mobile phase passes through a porous gel, larger solute molecules pass through the white spaces, while the smaller molecules are entrapped in the pores of the gel beads. Now imagine if you have a polymer research lab or a macromolecule research lab, and you have designed few materials, few molecules, and you are interested in separating these molecules depending upon their size. What would we do? We would execute them through this size exclusion chromatography, where these molecules, these materials can be easily separated depending upon their size. So this is how a simple technique based on the size exclusion can be applied to a novel technology, that is size exclusion chromatography technology. Going a step ahead, this is one of the most anticipated, maximum used type of a chromatography, which is bonded phase chromatography. What we are today using in most of the pharma industries in Gujrat country and worldwide through HPLC, GC, mostly people use bonded phase chromatography. Always remember, before we go on to the detailed discussion, in the bonded phase chromatography, the bonded phase is nothing but the stationary phase, which is made up of two different materials. It can be a polar material or it can be a non-polar material. Remember very well that if your column, your stationary phase is made up of a polar material, then among the matrix, that is the mixture of compounds, mixture of analytes that you are planning to separate, if your column is polar, if your stationary phase is polar, then among the matrices of the material, the most polar material will be separated out first. And the polar, as the polarity decreases, the separation also keeps on changing. Now, we will first go through this animated video and then go to the technology based on this technique. If we look over here, This is silica, and this is a non-polar chain that is binded to the stainless steel inner walls of the stationary phase through the silica. So the main part over here is the non-polar. But when we go opposite to it, that is normal phase chromatography, that is bonded phase, over here you can show there are cyano groups, and now it becomes polar. So whenever we are talking of bonded phase chromatography, there are two most required things. That is a stationary phase, which is non-polar, a stationary phase, which is polar. If the stationary phase is non-polar, we coin it as reverse phase chromatography. If the stationary phase is polar, we coin it as normal phase chromatography. So these reverse and normal phase chromatography are generally used to identify, separate, quantify organic molecules that can be used in pharma, medicine, drug, chemicals, food products, and for fewer times in petrochemical industries. So let us see the technological advancement based on the mechanism of separation, that is bonded phase chromatography. So boils based on the polarity, that is attraction. Reversed phase chromatography has a non-polar stationary phase and mobile phase is polar. Whereas for a normal phase chromatography, the stationary phase is polar and the mobile phase is polar. Now comes the question that where can this technology be used? Let us take three examples. Example number one, if I have a mixture of phenol and benzene, and industrially I want to quantify them and separate them. First of all, check for the compound, phenol and benzene. We can very well identify that among phenol and benzene, phenol will be more polar, benzene will be less polar. If I choose reverse phase chromatography, my stationary phase will be non-polar. So when my stationary phase is non-polar and I allow the mixture of benzene and phenol to pass through it, benzene will get more attracted towards the stationary phase. So it will remain intact inside, whereas the phenol will pass through. So this is the technological advancement that can be used to aggregate, separate the compounds from the matrix. Similarly, let us take another example. If we have two compounds that are very much closer to each other, and now we are interested in separating them, then only this technique won't be useful. But along with this technique of bonded phase chromatography, we need to add HPTS. That is when we have mixture of natural products that have been extracted from the plant powders. Generally, we go for HPTLC so that the compounds having similar nature based on their physical properties can be easily separated using this easiest technique. Friends, this is where chromatography plays a very important role when we try to distinguish two compounds falling in a similar quality of physical properties. Mind well, these techniques are more physical separation. So we have always mentioned that chromatography is a physical method of separation. Moving ahead with the bonded phase chromatography to affinity chromatography. This is purely based on the functional group and its binding with the surface. Let us first see the video. Before I play on with the video, if you look over here, these different shape structures suggest different compounds. And over here on the surface, if you see this U-shape yellow part is a specific shape which can only bind with a specific shaped compound. When we will play the video, you will get an idea that among all the compounds that are passing through the column, only the shape selective samples are getting binded and the rest are passing through. How can this be justified? Sometimes when you are trying to select or separate compounds of a particular nature, of a particular type. For example, I want amines to be trapped inside the column, and I don't want other compounds to be trapped inside the column. I will take stationary phase made up of such a material that has maximum affinity, maximum attraction towards amines. So what would it do? It would attract to the amines with the most probability, and it will not attract with the other materials. So the other materials will very easily pass through, whereas amines will be getting trapped inside the column. Moving ahead, you could see over here that these yellow color stationary phase indicators are placed on a resin materials. So this resin is a surface on which the yellow indicators like material, a stationary phase is placed through which when samples are passed, they can be easily separated. This has a very technological innovation and application. It is highly selective type of chromatography that is based upon the specific interaction between the analyte molecule and other compatible immobilized on the stationary phase. I have a very good example over here. For the separation of antigens, an antibody may be immobilized on a matrices that forms a stationary phase. In the drug chemistry, if I am interested in trapping an antigen, the correlated antibody can be selected as a stationary phase, and when this antigen is passed from the matrices through the column using a mobile phase, this particular antigen will get trapped with the antibody that is immobilized, that is stationary inside the column, and the rest will not. When a sample consisting of mixture of protein is passed through the column, only the specific antigen among those proteins, among those targets, will bind to the antibody that is immobilized on the stationary phase, and the rest will not get attracted. So this is how we can utilize 6 different techniques turned today into technology. So these are few of the technological innovations that came up with a very simple separation chemistry, rather to say a chromatography technique, which has today resulted into different technological based innovations and are used exclusively and explicitly in the industries to separate a specific compound from a mixture. So coming back to the theme of this webinar, when we are interested in separating materials or identifying materials, these techniques based on chromatography can be very easily used to do so. So this 30 to 40 minutes of webinar is just an opportunity for me to disclose among the webinar participants that if we go into the detailed study of each separation technique, we can come up with a lot of innovations that can be used in future for identification, separation, and quantification. If we just think of the first drug that might come out very soon that can combat COVID-19, once the drug is built up, we all know that the purity of the drug has to be checked through one of the technology based on chromatography technique. It might be HPLC, might be GC. So always remember, whatever be the material, once we are thinking of its purity profiling, along with the spectrophotometric or spectroscopic technology, it is always essential to have a separation technological advancement, and therefore always be confident that any technique that comes out from the separation side of chemistry, that is chromatography, will surely have its weightage on the future research on the materials that are to be identified. So these are some of the techniques that I disclosed over here, and these are some of the very related references from where I took few of the points. Apart from that, I have used the videos from the NME ICT portal, which has the maximum virtual videos that can be used. I am more engaged with my UG students, so I always keep my presentation simple so that it can reach to the students via we teachers. Thank you once again to the institute and especially to Dr. Kosti for giving me this opportunity to be with you all. Thank you one and all. The session is open for questions. Thank you, sir.
Thank you so much, sir.
Thank
You
you,
have-
Doctor. Thank you, Dr.
Thank you, sir.
Deepkumar,
Thank you, sir.
for your scholarly talk. Now the session is open for discussion. Dear participants,
Thank you, sir. I have one question. Can I ask one question, sir?
Yes, sir. Please.
Sir, it was a really very nice animation, very easy to understand. I hope there are many students they have joined here. My question is, as far as fingerprint of herbal extract it is concerned, so are there any specific chromatographic simple tests so that on spot, on field, we can carry out?
Sir, for herbal research or plant-based research, we can go in two different ways. One is chemical analysis, second one is physical analysis. We will not fall into spectroscopic analysis as of now, as the discussion and the question is pertinent. If we go for chemical analysis, we can test the flavonoids, the alkaloids, and the pigment content present. But pertaining specifically to your question, I would suggest that once we have a natural product extract with us in a test tube, let us take a lengthened stationary phase and put the spot at the bottom and make it run in different solvents. Nevertheless, it will not give us a perfect result, but it will help us identify the number of spots. And then this particular sample has to be placed in a widened column, not in a lengthened column, but in a widened column. We generally say when the column is lengthened, it is TLC. And when the column is widened, it is HPTLC. So I would suggest a combination of TLC and a HPTLC, that is a vertical and a horizontal chemistry of separation to work with the natural products. I have got very good results when I work in my laboratory with the CAMAG HPTLC, and we have separated few very good products.
Okay, thank you. One more question.
Yes, sir.
As far as organic farming is concerned,
Yes, sir.
so if a particular farmer wants to export his croppings to abroad countries, it needs certification from organic farming. So are there any simple tests?
Sir, if we are talking of exports,
Yes.
it means we need such tests where we can have not the purity profile. Sir, if you will look towards the newspaper, people today, industrialists today are not interested in purity profile. They are interested in impurity profile. If you will say, sir, my product is 99.7% pure, they will reply us in the mail, what about 0.3%? So when we are talking of exporting, that farmer has to invest a little higher amount. And as we know that all the CSIR lab across the country are very supportive when it comes to farmer and students. So when we are talking of farming, farming related products, farming related crops, the main concern globally would be pesticides.
Yes.
So according to me, if the pesticide is of a non-volatile nature, HPLC would be one of the best output or technology. But sometimes if we are talking about those tricky aerosol based pesticides which induce non-natural color to the material, to the farm products, then we have to think of a bit of GC. But my weightage would be, if for exporting, we cannot go for simple technology, because those people abroad will ask for impurity profile for sure. So we should have a technological advancement, and in case of identification of pesticide based impurity, for sure HPLC will definitely work.
Okay. Thank you, sir. Thank you.
Thank you, sir.
Can I ask one question?
Yes,
Yeah,
please, sir.
sure, sir.
Thank you, Dr. Joshi. It was excellent, and after a long time, I had refreshed my own information as well. Excellent. Okay, I have one basic question. Although I feel that without chromatography, no one would be doing research
No
today.
research.
Everything goes into the lab that goes via the chromatography. But I'm asking about in two different techniques. One is chromatography, other one is membrane separation, for example. So when it comes to the water purification, where do you see the future? It's chromatography or it's a water purification in membrane separation? Because in one case we have to consider the separation, and in other case we deal with the size exclusion. For example, if you take the example of seawater, there it works in the size exclusion principle. So what is your thought on that?
Sir, I have two different thoughts pertaining to purification of water. Let us first talk on membrane technology, because I had an opportunity way back in 2010 when I completed my master's. I am from Bhavnagar, that is CSM CRI CSIR lab, and I had an opportunity to work for a very little time in one of the membrane technology lab. If we are focusing to serve the society by providing the drinking or potable water, our concern is to remove all the impurities that are inorganic impurities, that can be physical impurities. In that case, very well, membrane technology will be useful. But in that also, sir, we need to implement two technologies. If we are talking about the salt impurities, that is the cations, especially the cations, then we have to think for ion exchange chromatography. Even today, there is a huge problem. At present, I am in a place called Patan. It is in the North Gujrat province of the state of Gujrat. It is a place where there is a belt, where there is a stretch of the land which has fluorine content, F content. And we know that excessive fluorine content is very harmful to the bones and to the teeth. And since last 10 years, the BRNS, Department of Atomic Energy, has become very sensitive on this issue. And they are releasing funds on the project based on the identification and removal methods of fluorine, mercury, and lead from the water to make it potable and drinking. In this case, when we are going for fluorine or fluoride, rather anion fluoride, we need ion exchange, sir. But when we are going for heavy metals, only ion exchange would not work. We would need a blend of two technology so that these heavy metals can be trapped based on their weight as well as based on their charge. So this is one way of answering, where membrane technology would be the base and chromatography would be a subsidiary. But if we think of a reverse case where we are just going into research, we are not much thinking initially regarding the social benefit. Let us keep it secondary. Then in my point of view, or what I am thinking, ion exchange chromatography for removal of cations and anions and removal of few undesired protein, undesired targets, undesired macromolecules, or undesired polymeric impurities. We definitely have to go through size exclusion chromatography or gel permeation chromatography. But seeing to the future, what I think, there should be a blend of both. Because when you are going for some membrane technology, I am quite sure that let it be the very basic honeybee comb structure in the membrane technology. Why can't we insert the trappers or the stationary phase into that membrane technology? So pertaining to your question and seeing to the future, my point of view or my stand would be a blend of chromatography to be inserted on the membrane technology with a single aim of advancing technique into technology and technology into only quoted social services.
Thank you. Thank you so much.
Welcome, sir.
Thank you, sir. There are lot of questions before going to that. Dr. Deepkumar Joshi, very excellent talk. I think all of guys understand all the chemistry, type of chemistry and their use and all. So I have some question I took from YouTube stream as well as Zoom chat box. The first question is from Dr. Santosh Kamble from YCIS Satara. He's asking that which compound are used for the separation of indicator in a paper chromatography.
Okay. When we talk of indicators, we have to look for the functional groups of the indicators. Let us assume an indicator which has a polar substitutions. It means our indicator is polar by nature. And if we want to separate or capture such type of indicator, we must take a polar column where this polar natured indicator would be trapped on a polar column. But let us think of an indicator which is a salt-based indicator. When we talk of a salt-based indicator, it will have charge. And when we have charge, we have to think of electrostatic chromatography.
Thank you, sir. Thank you so much. The next question from YouTube stream, I took Athevale, if I am wrong, please sorry to his question that each electrophoresis based on the affinity chromatography. I will repeat if
I got it.
okay.
See, whenever we are talking of electrophoresis, it involves charge also. It involves charge also. So apart from affinity chromatography, in my view, you must even think during electrophoresis a little bit about the charges. That is the electrostatic interactions that can be involved in a chromatography technique. And in this particular question, I would suggest that I would share one of my lecture to Kosti sir and request sir to forward it to the participants. In one of the online lecture series on chromatography, I have discussed 5 to 7 minutes, especially on this question and its technological application.
Yeah, thank you, sir. Once you send to me, I will definitely hand over to our participant. Another question from Vikas Shukla. He is asking that what are the disadvantages of size exclusive chromatography?
Sometimes what happens in size exclusive chromatography, let us assume that we have two different compounds which are differently natured but have a very less difference in their size. Then it becomes very difficult to separate them from this porous material. But in such a case, if we think of another practical application, that is as they two have different nature, let us go for the nature-based chromatography, that is stationary-based bonded phase chromatography, or let us think of affinity chromatography, then it will be more easy. In a shorter way, in a nutshell, I would like to say that whenever we are working on a macromolecular substance or on a polymeric substance or on a heavyweight substance, do not depend on one technique. Definitely, one technique is useful. But when there is a mixture of two or more similarly sized compounds, always keep another window open so that if one technique does not work, another works. Because first, when technically our things go right, then and then only we can go for technological advancement.
Thank you, sir. Last question from Sudha Sulia. She is asking that in bonded phase chromatography technique, how to polar suitable separate. If you understand, then okay. Otherwise, I will repeat.
No worries, I got it. See, whenever we are talking of bonded phase chromatography, first of all, we need to think of two things. Two different nature of the stationary phase. It can be hydrophobic, can be hydrophilic. When we are talking of hydrophobic, it is non-polar. When we are talking of hydrophilic, it is polar. So, if I understand the question, if you are interested in separating a polar compound, it is your choice. If you want to keep initially the compound trapped into the column, please use polar column for a polar compound. But if you want to remove the compound out quickly, then you use a non-polar compound. But I would suggest that when you are interested in separating a compound, keep correlating nature between the analyte and the column. Sudha.
Thank you so much, sir. I think there are 2, 3 questions more, but I will send to you, sir. And because the time is running, so that's what we are avoiding those things.
No worries.
Thank you.
Very nice talk.
Thank you so much, sir.
Thank you, sir.
Very outstanding talk, and personally, I feel that I revise all the chromatography. Now I hand over to Dr. Lokde, sir. I can coordinate.
Thank you, sir. Thank you, Dr. Deepkumar, sir, for your well-versed and scholarly talk. Thank you very much. Now I invite Dr. S.D. Jadhav, Professor and Head, Department of Chemistry, University College, Koregaon, for his concluding remarks. Dr. S.D. Jadhav, sir, over to you, sir, please.
Okay. Thank you, sir. Just now we have listened Dr. Deepkumar Joshi, who have delivered a talk on chromatographic techniques in very beautiful animated way. Nice presentation, very much learned personality, and definitely I would like to personally communicate for his guidance in our next project. I would like to also thank Dr. Pachfule sir, who highlighted graphene, nitinol, alloys, zeolite, and more emphasis on metal organic framework, then disorder and order stability, hydrogen gas storage, and so on. So, I think both of resource persons, they have delivered very nice talk, nice presentation, and I am very much happy to inform you, all the participants, that more than 1.6 K participants, they have been joined here, and I think it is a grand success. I also thanks Principal Dr. Vijay Singh Sawant sir. He is always supporting to us. Then Joint Secretary of Prayat Shikshan Sanstha, Dr. Pratibha Madam, who had given best wishes for this international webinar. So thank you very much, all participants and all my backstage artists. Thank you very much. Thank you.
Hello.
Thank you so much, sir.
Thank you, sir. Thank you, Deepkumar sir and Pradip sir. Now, there would be the last event of formal vote of thanks. And for that, I invite Dr. N.D. Nikam, Assistant Professor, Department of Chemistry, DP Bhosle College, Koregaon, to propose vote of thanks of the eminent scholars, participants, and rest of the people who have been joined this webinar. Over to you, Dr. N.D. Nikam.
Thank you, Lokde, sir. Good afternoon to all of you. I am Dr. N.D. Nikam, working as Assistant Professor in Department of Chemistry at DP Bhosle College, Koregaon. Today we have organized a one-day international webinar on hyphenated techniques in detection of smart materials in collaboration with Technical University of Berlin, Germany. It's a kind of privilege to me to express my thanks to Dr. Pradip Pachfule, Department of Chemistry, Technical University of Berlin, Germany. He delivered a lecture on photocatalytic hydrogen generation, and gave information about smart materials, carbon-based smart materials, graphene-based smart materials, microporous polymeric materials, metal organic framework, and covalent organic frameworks. Thank you, sir, for your valuable guidance, your informative lecture. Thank you so much. I extend my thanks to Dr. Deepkumar Joshi, Department of Chemistry,
Sheth M College, Patan, Gujrat, for enlightening us on the topic of chromatography and giving us information about various techniques of chromatography like partition chromatography, separation chromatography, ion exchange chromatography, size exclusion chromatography, bonded phase chromatography, and affinity chromatography. Thank you, sir. You give us so many information about the basic chromatographies, the techniques which are useful for the separation of components. Thank you, sir. I am very much thankful to Honorable Principal Dr. P.S. Gaikwad Ma'am, Joint Secretary, Higher Education Raj Shikshan Sanstha Satara, for her motivational message and valuable inputs for the success of this webinar. Thank you, ma'am, for your kind presence. I express my thanks to Principal Dr. V.S. Sawant, sir, who motivate us and guide us to conduct the webinar. Thank you, sir, for your kind support and always being with us. I am very much thankful to all the participants who take part in this webinar worldwide. We have more than 1,700 participants through Zoom and YouTube. They are live YouTube and 28 from abroad. I thanks to all the participants who take part in this webinar, who make success the webinar internationally. I express my gratitude towards Technical University of Berlin, Germany, for providing collaboration to organize such kind of international event today. I am thankful to all of those who take part in this webinar and help us to make success this webinar. Thank you so much to one and all. Thank you so much.
Thank you, Nitin sir. Now it's a request to all the participants that they have to fill in the feedback form and submit your feedback. After submitting your successful feedback, you will receive your certificate of participation on your email ID provided while registering for the webinar. And if there are some other instructions, over to you, Dr. Kosti sir, please.
Thank you so much, Dr. Lokde sir. There are few additional information here. If you, for the certificate, you have to register and you have to fill the feedback form. Then only you will get the certificates. This is the mandatory to register, and you have to fill the feedback as well. Then you will get the certificate on your mentioned email ID. While filling the feedback form, you have to mention your information very correctly, because the same information will be appear on the certificate. If there is a mistake from you, then we will not entertain with those, because this is the e-certificate. So please take care while submitting feedback form. So these are the information from my side. Thank you so much.
Hello. As the participants are large in number, uh, some participants will get certificates today itself, and then some of the participants will have to wait for the Google to issue certificate to you. Okay, thank you very much.
Thank you, sir.
Hi, teacher sir.